doing some further analysis in part 2 of this lecture. Now, having Km and Vmax are great, but we need to be able to interpret them and kind of compare apples to apples. Enzymes have a wide variety of characteristics, and we need to be able to compare them. So Km can vary for different substrates, even within the same enzyme. So hexokinase, it can use ATP, glucose, fructose, but the Kms for all of these are different. So it's kind of difficult to compare Km, because Km can mean something different depending on the actual mechanism of the enzyme. Now let's say that you actually have a reaction with 2 steps. The Km is kind of a catch-all for a more complicated equation that involves all of the rate constants. Remember, the lowercase k that is italicized is a rate constant. In this 2-step mechanism that we're talking about, we've got enzyme plus substrate reversibly forming ES. And from there, we're forming E plus P. Now, sometimes you'll see this as just a single arrow where it's irreversible to go from ES to EP. But this is the 2-step mechanism that we're talking about. And to fill in our K values, this is K1, K minus 1, K2, K minus 2, which we're not really talking about yet. Why does this matter? Well, the Km is relating the breakdown of the ES complex. So the ES complex has 2 choices. It can either break down and make the enzyme plus the substrate, so it just falls apart, or it pushes forward, does some chemistry, and releases a product. The Km houses all of the rate constants that have to do with that decision of the fate of the ES complex. So it's K2 plus K minus 1. So that's the 2 different routes that the enzyme substrate complex can take, divided by the formation of ES. If K2 is rate limiting, then that means that K2 is small, right? It's going to be smaller than the other rate constants. And if it's much smaller than K minus 1, then that means that we can essentially ignore it because K2 is so small that it's practically like adding 0. So in this special case, where K2 is much, much smaller than K minus 1, we can get rid of it and simplify the Km equation to K minus 1 over K1, which is defined as the dissociation constant, Kd, of that enzyme substrate complex. But this is a special condition. Cannot stress that enough. This is a special condition. It is not always the case. But under these special conditions, the Km represents a measure of the affinity of the substrate for the enzyme. But only under these conditions. If someone says that the Km measures affinity, blanket statement, always and forever, no. You tell them no, you shake your finger at them. That's wrong. Km is not always a measure of affinity. Go back to school. So we talked about Km and how to interpret that. Now we're going to talk about interpreting Vmax. So Vmax tells you the number of reaction steps and the identity of the rate limiting step, right? So all things are there from enzyme to enzyme. But Vmax tells you the velocity of your slowest step. And for that same 2-step Michaelis-Menten mechanism, the Vmax is going to be equal to K2, remember that's our slow step, times the total enzyme concentration. Because the total enzyme concentration, if you're under Vmax conditions, means that all of your enzyme is engaged and active. When product is released, it's rate limiting. And that is a little bit different from the Michaelis-Menten, going from ES straight to E plus P. It introduces this step of product release. So we now have this K3. And in a lot of enzymes, product release is actually rate limiting, not product formation. So everything up to here is very fast, and then everything after that is slow. So when we're talking about Vmax, it's not always going to be the formation of product. Oftentimes it's actually going to be the release of product, because that is the slowest step, and that is usually rate limiting. But again, it depends on the enzyme. While it is common, and it is a fair assumption to make, you cannot just go with that assumption as a blanket statement. It's like stereotypes. They may describe a certain portion of the population, but it is not true for everyone. It just may be common enough to where it becomes kind of common knowledge, but it's something that you should not expect to always be the case. So how do we look at KM and Vmax? How do we look at these things as apples to apples and have a fair comparison? Well, let's introduce KCAT. Okay? It's a general rate constant that describes the limiting rate of any enzyme catalyzed reaction at saturation. So that means that the limiting step could be any step within this whole process, and we can call it KCAT. That's the understanding. So one step in a multi-step reaction is clearly the limiting step, then KCAT is going to be the rate constant for that step. But things are usually more complex than that. And you can actually have several rate limiting steps where you have a lot of fast steps and a lot of slow steps, and all the slow steps are about the same rate. If we know that KCAT is the rate under saturation conditions, said that Vmax is equal to our K, it was K2 before, times the enzyme total concentration. But if this is the rate limiting step, then we can actually call that KCAT. So our new equation, let me do a color other than black. Vmax is equal to KCAT times the enzyme total. And if you rearrange those, then you get Vmax over the total enzyme concentration is equal to KCAT. And if you know that, then you can substitute in. And that is another very useful form of Michaelis-Menten when it comes to graphing your data. KCAT is also called the turnover number. So it tells you the number of substrate molecules that you convert to product in a given unit of time. Usually it's per second, but it could be per minute, if it's a slower enzyme. Catalase is something that usually you play with in biology or like a low-level chemistry class. It takes hydrogen peroxide and it makes water and oxygen. It is stupid fast, okay? KCAT, out of this world. Carbonic anhydrase is something you've also seen that's in relation to blood, so it makes bicarbonate. You don't have to know any of these KCAT or turnover numbers. It just gives you kind of an idea of the range that you can see. If you compare the ratio of KCAT, okay, you don't have to. To know any of these KCAT or turnover numbers, it just gives you kind of an idea of the range that you can see. If you compare, you know how have to know any of these kcat or turnover numbers. It just gives you kind of an idea of the range that you can see. If you compare the ratio of kcat over km for two reactions, that's the best way to compare, the catalytic efficiency. And that's usually what you'll see it termed as. You'll see catalytic efficiency, and they're referring to kcat over km. And what this does is it allows you to compare the conversion of enzyme plus substrate to enzyme plus product. If you have a substrate concentration that's much less than your Km, then you can actually substitute in kcat over Km times your enzyme total times your substrate concentration, and that can also be very useful for representing your data. So you don't memorize this. This is a combination of things that are helpful in the lab and things that you'll need to know for your exam. For your exam and just for your general knowledge, it's going to be much more basic, but I'm going into further detail here just because it's so rich. And if you're actually interested in doing enzymology, maybe you want to do an MD PhD program or you want to do research as a job, then hopefully this will give you some tools that you can be competitive in those markets. So kcat over Km is actually a second order rate constant. So it's got the units of per molar per second, and the upper limit that you'll see for kcat over Km is about 10 to the 8th, 10 to the 9th. That corresponds to the diffusion limit. So how fast something, a molecule can kind of wiggle around and travel and end up somewhere else. Okay? That's the diffusion limit. Kcat over Km is a value that you can achieve with a mixture of kcat Km values. So you may have, a relatively fast, slow step, but, your Km is a little bit on the large side. So there's lots of different combinations of kcat and Km that can get you the same catalytic efficiency. Lots of enzymes actually catalyze reactions with two or more substrates. So Michaelis-Menten is great for one enzyme, one substrate. But large majority of them have at least two substrates and two products. So when we were talking about that covalent bond forming with the enzyme, we're talking about kind of two different substrates. You're forming a bond between the enzyme and some other group, like a phosphate group, perhaps, and then you can transfer that onto a substrate. So that would be an example of a covalent mechanism. And you have two substrates, the thing that's providing the phosphate and the thing that's getting the phosphate. You can also have redox reactions. You've got something being oxidized, something being reduced. So multiple substrates. And some reactions involve ternary complexes. So you've got enzyme, it binds substrate, it binds another substrate, and then it does some chemistry. So the Michaelis-Menten it's very powerful, but there are some limitations. You can kind of chop up an enzyme mechanism into pieces and make it fit the Michaelis-Menten model or theory so that you can do the traditional steady state kinetics. But keep in mind that biology is never that simple or easy. It's complex because we're complex. So you can have different modes of binding, like ordered versus random, and you're not responsible for knowing that. But just understand that there are mechanisms out there where enzymes do a lot of things that don't fit neatly into the Michaelis-Menten theory. Some enzymes don't even form a ternary complex. So you might have binding of a substrate, and then you make a product. There's some kind of change to the enzyme, and that product leaves. Then you have a second substrate bind, and then maybe your enzyme transfers a group onto that second product, or second substrate, and then it's regenerated. So there's lots of different caveats. And again, not going to hold you to knowing all the different mechanisms like ping pong or double displacement or anything like that. Just have a general understanding that there are enzyme reactions that don't fall neatly into Michaelis-Menten bucket. That's it for part 1. Make sure that you tune in for part 2, where we start with pre-steady state. Hey everybody, part 2 of chapter 6. If you did not watch the part 1 video, you need to stop this right now and go to the part 1 video. We'll continue our discussion of enzyme, and we talked about steady state. That buildup of upflow device allows you to very rapidly mix your enzyme and substrate and quench the reaction, usually with acid. And you can sample really, really quickly, so you can see absorbance or fluorescence or whatever signal you need to see. And we're talking about looking at, milliseconds or seconds, very, very small snippets of time, and you're taking a lot of data points in that snippet of time. There is something called kind of the dead time, which is the amount of time that it takes for the detection to actually hit in small snippets of time, and you're taking a lot of data points in that snippet of time. There is something called kind of the dead time, which is the amount of time that it takes for the detection to actually start. So in between the mixing of the substrate and the enzyme and the detection, that's the window of dead time where there's reaction happening, but you're not actually looking at a signal for it, your fluorescence or absorbance. And really expensive stop flows will have like a super teeny tiny amount of dead time so that you're not missing any details. Oftentimes for a lot of enzymes, dissociation of the product is rate limiting. So if you have this scenario, instead of going straight from, and I'll write up the two-step scenario we were working with last time, where you had enzyme binding to its substrate and forming that ES complex, and then we just said, okay, that's gonna break down to enzyme plus protein. That's our two-step mechanism. In reality though, most of the time you're gonna form this enzyme product complex, and that's actually gonna happen pretty quickly. That's where you're doing the chemistry, and you form this enzyme product complex, but releasing the product is slow. So this last step is very slow. So in this scenario, in this mechanism that we have, K3 is rate limiting. We can use pre-steady state kinetics to determine the rate limiting step. So if you see a burst, then that means that you have a rate limiting step. It doesn't tell you which step it is, but it tells you that you have one. So you're rapidly mixing, again, your enzyme and your substrate, and then you're quenching with acid after a short amount of time. You'll notice that for each of these, there's kind of, so with the other, with the steady state, we would say, okay, we're gonna take our tangent from time 0, and that's gonna be our initial velocity. But here, the time is so short that we shouldn't see any kind of initial velocity and then kind of a tapering off, because we're doing a really short time frame. So we should just see some kind of linear increase. If we don't, then that means we have a burst. That's called a burst, and we have a rate limiting step that you can determine. And the beauty of this is that you know that this rate limiting step occurs after you've started monitoring product formation. So that means that you may be made your product and it hasn't been released yet, or maybe you made your product and it's been released, but your enzyme and substrate require some kind of conformational change that's slow. So these are all things that you can't really determine with Michaelis-Menten or steady state kinetics. Oh, one more note. So another shout out. So this is actually from a paper from my thesis lab. It's in your book. This enzyme is, we're looking at RNase P. And this figure is from a paper from my thesis lab. So yeah, y'all, I'm legit. I went to school. Okay. Very, very side note. Not gonna be on the exam, promise. So that's it for talking about analyzing kinetics in terms of just studying, basic enzyme chemistry. But another powerful tool that we can use are inhibitors. And this kind of helps you to look at, okay, how can I understand this enzyme a little bit better? If you can build something that inhibits an enzyme, then that means you understand its mechanism. And oftentimes the drugs that we use are inhibitors. So let's talk about how we can analyze the kinetics of inhibitors. So inhibitors are just molecules that interfere with catalysis. And there's two classes that we're going to talk about, reversible and irreversible. It's pretty self-explanatory. There's different types of reversible inhibition. How we can analyze, and oftentimes the drugs that we use are inhibitors. So let's talk about how we can analyze the kinetics of inhibitors. So inhibitors are just molecules that interfere with catalysis. And there's two classes that we're going to talk about, reversible and irreversible. It's pretty self-explanatory. There's different types of reversible inhibition. We're really going to focus on the first three. We're not going to worry too much about non-competitive inhibition. So competitive inhibition means that you have an inhibitor So competitive inhibition means that you have an inhibitor that binds the same spot as your substrate would. So if you have an enzyme that binds substrate S, your inhibitor, which is I, is going to bind to the same spot as S. So they are competing for the same spot in the active site. Competitive inhibition is a type of reversible inhibition. So it can bind and be released just like a substrate. You're going to see this alpha prime. We're not going to talk too much about alpha prime and you know, the specific numbers of how an inhibitor affects certain parameters, kinetic parameters, but we will talk about the fact that competitive inhibitors affect the apparent Kn. So you don't need to know about, again, this alpha in terms of by how much. But just know that competitive inhibitors affect the apparent Kn, but they don't do anything to the Vmax. What do we mean by this? The apparent Kn is the experimentally determined Kn when you have your substrate and your inhibitor present. So if you have substrate present with your inhibitor and you have a really high concentration of your substrate, you can still see normal kinetic behavior. You see the normal Vmax, but you will notice that your Km has increased. That means that you need more substrate than you normally would to reach the same velocities. And that makes sense because you have an inhibitor that is competing for that same spot, but you're not doing any chemistry. When you're looking at a Line-Weaver-Burk plot, which remember that's also called a double reciprocal plot, you can actually see when you have a competitive inhibitor. When you're looking at a Line-Weaver-Burk plot, which remember that's also called a double reciprocal plot, you can actually see when you have a competitive inhibitor. When you have a competitive inhibitor, 1 over Vmax, which is your y-intercept, doesn't change. But if you look at the x-axis, we no longer have the same negative 1 over Km value. So your Km has changed. And anytime you see that, you know you're dealing with an inhibitor. The next type of inhibition that we'll cover is uncompetitive inhibition. And that means that you have some molecule that binds at a site that is distinct from the substrate active site. So you can still have your substrate bound to your enzyme and the inhibitor combined at the same time. And when it does, it inhibits. So a difference between uncompetitive and competitive, in addition to the fact that the binding site for these inhibitors is different, the uncompetitive inhibitor likes to bind the ES complex. It's still reversible. So if that inhibitor falls off, then you can still have some kind of catalysis occur. But that inhibitor will bind the ES complex, and it is frozen in time until that inhibitor leaves. Uncompetitive inhibitors affect both the apparent Km and the Vmax. So your Vmax is going to decrease, and your apparent Km is going to decrease as well. This is what it looks like on the double reciprocal plot. Your apparent Km is going to decrease as well. This is what it looks like on the double reciprocal plot. All of your y-intercepts for the different concentrations of inhibitor are different. So that means your Vmax is different. And we see the same thing with our x-intercept. They're all different for the different concentrations of inhibitors. With mixed inhibition, we're again looking at a site that is distinct from the substrate active site. But it doesn't really mind binding to the enzyme or the enzyme substrate complex. It doesn't care. It'll bind to either one. It doesn't care. It'll bind to either one. Usually you'll see an effect. Inhibitor falls off. means that you have 1 over K, finally, but you're not doing it in chemistry. And that makes this site and be relieved by concentrations of inhibitors. With mixed inhibition, we're again looking at a site that is distinct from the substrate active site, but it doesn't really mind binding to the enzyme or the enzyme substrate complex. It doesn't care. It'll bind to either one. Usually you'll see an effect on both Km and Vmax. So Vmax is affected because you're affecting the amount of enzyme substrate complex, right? Just like with the uncompetitive inhibition. You're effectively reducing the amount of enzyme substrate complex that can go forward and do chemistry. Your apparent Km may increase or decrease, and it really just depends on whether or not your inhibitor binds the free enzyme better or the enzyme substrate complex better. So that one you can't really say for sure, oh, the Km is absolutely going to increase every time or decrease every time. Again, we've got that Lineweaver-Burke plot, and we've got a change in both the Vmax and the Km. The lines intersect still, but we're looking at an intersection that's to the left of the y-axis. So they do converge, but not on that y-axis. So those are the reversible inhibition types that we're going to talk about. Now we're going to move on to irreversible. Irreversible inhibitors bind covalently, or in essence, they just destroy the functionality of the enzyme. So they'll bind tightly, covalently, or they form a really stable complex, and it's a non-covalent interaction. But it is effectively, this enzyme is no longer available. That inhibitor is not going to release, so it's stuck, it's dead. You can have what's called a suicide inactivator, which is also called a mechanism-based inactivator. And what that means is you have an inhibitor that will undergo a few steps of catalysis, so it'll go through maybe the first 1 or 2 steps to convert A to B, but then it becomes covalently attached, let's say. So in this example, we've got serine 195 of an enzyme. We're going to talk about an enzyme that uses a serine 195 for catalysis coming up. But if you have this enzyme that I'm going to leave nameless for now, and you add in an inhibitor, it can undergo part of the mechanism that it normally would do, and then it gets stuck. So that is a mechanism-based inactivator. Transient state analogs are also really great irreversible inhibitors because they're designed to resemble the transition state that an enzyme would already be trying to achieve with its substrate. So you have this transition state analog that is complementary to the enzyme. Remember, the enzyme is not 100% complementary to its substrate. It's complementary to the transition state. So if you have something that looks like the transition state, it's going to bind really tightly. And you don't have to have a covalent interaction for that enzyme to hold on to it forever. Now we're going to move on to what I think is a really fun part of this chapter, looking at an example of enzymatic reactions. We've done all this talk about theoretical stuff. Now we're going to look at some actual enzymes. The first one we're going to talk about is chymotrypsin. We brought up chymotrypsin a little bit here and there, but now we're really going to talk about it. Chymotrypsin is a protease, and that means that it's an enzyme that cleaves peptide bonds, and it uses water to do so. On the right, you can see kind of a topology diagram for part A, and then B, C, and D all give some detail about the protein structure. And D in particular is what we're interested in, because this shows you the active site. The residues that are in the active site are shown in red in the topology diagram. So all those really key ones are highlighted. You'll also notice some of these structural components here. There's some disulfide bonding going on to stabilize the conformation of this protein. Just a side note. Chymotrypsin is a serine protease. So a serine residue in the active site is the nucleophile for the reaction. If you remember your organic chemistry, you probably heard the term nucleophile quite a lot. The nucleophile is the oxygen that's on serine 195. So remember that serine has an OH, and that oxygen is the nucleophile. The active site contains what's called catalytic triad, and you'll see that in serine proteases. And it's just the network of hydrogen bonding that enables serine to be a really good nucleophile. So in this case, we've got serine, we've got histidine, and an aspartame. And we need all three of these for activity. There's two phases in this mechanism. The first part is the acylation phase, and that's when the peptide bond is cleaved. So you have a peptide substrate that binds, and you cut that, and you form an ester linkage between that peptide carbonyl carbon and your enzyme. So what that means is you've got an enzyme, and remember that serine 195? So you've made an acyl intermediate, okay? You've got part of a peptide that was part of your substrate. It is covalently attached to your enzyme. In the second phase, you have the deacylation phase. And this one uses water to cleave that bond. So that's the second phase. You cleave that bond, and you liberate that piece of peptide, and you regenerate serine 195. Now, just as a little bit of practice, after listening to this description of the mechanism, think about the kind of catalysis that might be. We talked about general acid-base catalysis, covalent modification, and we also talked about metal. Ion catalysis. So think about what kind of catalysis this might be. Metal ion. Catalysis. So think about what kind of catalysis this might be. Now we're going to step through the mechanism. I'm not going to expect you to push the arrows for this particular reaction, but I do want you to understand overall how it works. We're going to get to some arrow pushing, more in metabolism. This is the warm-up. So this is an active site cartoon for chymotrypsin. We've got all of our players here. There are two other key aspects of this active site. The first is the hydrophobic binder. This is necessary for binding of the substrate. Chymotrypsin likes to cleave after aromatic residues. And that aromatic residue, the R group, is going to nestle in quite nicely here in this hydrophobic pocket. It's going to hold on to it. The other thing that this active site has is what's called oxyanion hole. And this is the place that stabilizes the charged transition state. So when we make an intermediate, before we cleave the first bond, that's where it's going to be stabilized. So we have a substrate bind. It's got an aromatic group. Aromatic group is nestled into that hydrophobic pocket. We've got the carbonyl of the peptide bond, the amide bond, secured with hydrogen bonding. It's positioned so that the serine 195 can act as a nucleophile.